All right, so today we're going to talk about the derivative of a function, which we've actually already talked about. We just didn't talk about it as a derivative. If the slope of a curve, y equals f of x, exists at x equals a, that is, the limit as h goes to 0 of f of a plus h minus f of a all over h exists, then this limit is called the derivative of f at a. So far we've been calling it the slope of the curve, or the instantaneous rate of change, or the slope of the tangent. Well, now we're giving it another name. It's just called the derivative. All those things equal the derivative at a point. So the derivative of function f with respect to the variable x is the function f prime of x. That's the way you read that, and that little mark is not curved, it's straight. That's how you read it, as f prime of x, whose value is f prime of x is equal to the limit as h goes to 0 of f of x plus h minus f of x over h, provided the limit exists. So basically the difference between those two is this is at a particular point. This is going to give me a function where I can substitute any x value in that I want and get the derivative at that point. Get the slope of the tangent line, the slope of the curve, the instantaneous rate of change of that curve at any point. If f prime of a exists, we say that f is differentiable at x equals a. And occasionally I have a student who, rightly so, might ask, shouldn't it be derivatable? Like you're able to take its derivative? And I'd be like, yes, but why are they using, differentiable? It's because this is the difference quotient. So that's where that comes from. Although I kind of like the word derivatable. It's fun to say.
Sounds like a real word.
It sounds like what?
Sounds like a real word.
It sounds like a real word. If we can get enough people to use it, we can get it into the dictionary. New goal in life. All right, so let's find the derivative of f of x is equal to x cubed. So when we do that, f prime of x will be the limit as h goes to 0 of f of x plus h, so that'll be x plus h quantity cubed, minus f of x, x cubed, all over h. So this will be the limit as h goes to 0 of, when we cube x plus h, we get x cubed plus 3x squared h plus 3xh squared plus h cubed, and then we have minus x cubed from before, all over h. I would imagine you guys are pretty good at squaring binomials, cubing binomials, and higher. Did you guys ever learn Pascal's triangle?
Yes.
Okay, and that's where the 1, 3, 3, 1 comes from for those coefficients. So that's going to be the limit as h goes to 0 of, notice the x cubed minus x cubed, that drops out. So I've got 3x squared h plus 3xh squared plus h cubed all over h. Again, as we've done numerous times now, since h is never equal to 0, it's just getting close to 0, it's legal for me to divide everything by h. So that'll be the limit as h goes to 0 of 3x squared plus 3xh plus h squared. And then as h goes to 0, the second two terms will drop out, leaving me with 3x squared. So the derivative of x cubed is 3x squared.
I feel like there's gotta be a faster way to do that.
Oh, there is. We'll learn rules for taking derivatives that don't involve using the definition all the time. That particular one, it's called the power rule, and it's really quick and easy.
Is it the one with the plus c
No,
that everybody forgets?
no. That's the antiderivative.
Uh,
We'll get to those a little bit later. So there's an alternate definition. Now, I'll just tell you up front, unless someone says use the alternate definition, I don't ever use it. But your book is occasionally going to ask you to use the alternate definition. And it's worth knowing, but in terms of do I use it for things? Probably not. Every now and then it's easier if you use the alternate form. So this says that the derivative of function f at the point x equals a is the limit f prime of a, which is equal to the limit as x goes to a of f of x minus f of a over x minus a. You're like, wait a minute. Okay. So what we're doing is letting x get really close to this a value. As x gets really close to this a value, basically we go from having something that would be a secant line, it's two different points. Now those 2 points are moving close together so that we have a tangent line now. Right, remember that, don't worry about writing this. We start kind of like this, and we have a secant, and we have the slope of the secant, and then what we're interested in is, well, if I move this point closer and closer and closer to this one, I get the tangent line instead of the secant line. That's what we're doing. So, I'm going to make a quick change to this one. We're going to use the alternate definition to find f prime at 4. So f prime at 4 will be equal to the square root of x minus f of a, so the square root of 4, all over x minus 4. So it's f of x minus f of a over x minus a. All right, well, if I try and substitute in directly, I'm going to get 0 over 0, which by this point we're like, yeah, I can't do anything with that. Got to do some more work. So we're going to multiply by the conjugate here. Multiply by the square root of x plus the square root of 4 over the square root of x plus the square root of 4. When we do that, we're going to have, I'm sorry, I left off my limit. This is the limit as x goes to 4. So the limit as x goes to 4 of, well, let's see, when I multiply these two together, I get x minus 4. And in the denominator, I have x minus 4 times square root of x plus the square root of 4. And now something lovely happens in that the x minus 4 divided by x minus 4 everywhere except for at 4 is equal to 1, and we're never at 4 here. So that's going to be 1 over, if I let x go to 4, that'll be the square root of 4 plus the square root of 4, which is 1/4.
And that tells us that the slope of the tangent is 1/4, right?
Right, the slope of the curve, the slope of the tangent, the instantaneous rate of change of the function at 4 are all 1/4. All right, so notation for the derivative. So for the function y equals f of x, each of the following denote the derivative. We've already talked about f prime. That's the way Newton wrote it. He also sometimes, since the f of x was equal to y, he sometimes would write it as y prime. Same thing. So these are all from Newton. You don't need to remember that, but that's what's going on. These are all from a different mathematician who developed calculus at almost exactly the same time as Newton, but he was on the continent, not in England. Leibniz. I know it looks like it ought to be Leibniz, but it's Leibniz because I think it's Germanic, and in German, when you have two vowels together, it's the second one that you say. In English, when you have two vowels together, it's the first one that says, says its name, I think is the rule you learn when you're a little kid. Like read, R-E-A-D, the E-A makes the E a long E. In German, it's the other way around. So that's Leibniz. Anyway, this is just read dy dx. He was thinking of this slightly differently, but I kind of like this because it reminds me of delta y over delta x, which is how you find slope. He actually thought of it that way, but he thought of it as an infinitesimal distance in x and another infinitesimal distance in y, and what is their ratio. Sometimes you'll see this, almost never actually. You will see this, d over dx f of x. This means take the derivative with respect to the variable x of f of x. So when you see it like this d over dx is an operator, like sine or the square root or anything else. It tells you to do that to what comes afterwards. All right, so estimating derivatives graphically. So one of the things that we should be able to do is, given the graph of a function, we should be able to pretty quickly sketch or picture in your head, well, what is the derivative of that graph going to look like? Here's what I do. If I have something like this, I'll first look to see, are there any places where the derivative is going to be 0? Now remember, the derivative is the slope of the tangent line. So what I'm thinking about is, well, where on here does the tangent line look like, if I drew it in, it would have a slope of 0? Yeah, at this top point and at this bottom point. Well, that one's at 4, so that gives me a point. Excuse me. And then up here somewhere, maybe it's at that point. That looks like it's a little bit more than 2. Gives me another point to aim at. Now, here's what I do to get just a real quick it takes a while to explain it, but a real quick idea of what the derivative is going to be at 0. So at 0, if you can think about what would a tangent line look like there, and if you actually have a ruler and can do it, you can get pretty good, but it's going to look something like that, right? I always make sure that I draw it long enough to where it goes one to the right or one to the left, because then I just draw in a little slope triangle, and I don't actually draw it, I just do this in my head. The slope triangle, at least. This is 1, and this looks like it's a little bit less than 2, right? In terms of the slope. So it went up a little bit less than 2 when it went to the right 1. So my slope is a little bit less than 2. When I'm over here, this slope, again, I just kind of eyeball it and go, okay. That slope, to me it looks like it's about 1.5. So I'm at x is 1 and this is 1.5. It's less steep here. When I get over to this point, if I draw in a tangent line, it's going to look something like that. It almost goes right along the curve right through there. That looks like about 1, 2, 3. That looks like it's about -3. And it is kind of in a smooth curve motion, connect them.
Where do you get -3?
So if I drew in that slope triangle, this is about -3 when this goes over 1. Now, if I'm sketching these, I don't spend nearly as long as I just did. When I'm sketching these, let me show you what I'm likely to do. I do the zeros. Looks like there's a 0 at 4 and a little bit more than 2. Over here, are the slopes of the tangent lines going to be positive or are they going to be negative? They're going to be positive. Okay. And I usually look for where is it steepest? Looks like it's steepest somewhere in here, right? It's hard to see exactly where it's steepest, isn't it? But I'll go, okay, about how much is that? And I'll go, yeah. I always want to make this distance 1, 1, 2, it looks like it's almost 3. And that's here, so right there, it's almost 3, and that's going to be my high point. And then over here, it's steepest, I don't know, somewhere right in here. And that's going to be my low point. And I don't know, that looks like that's about in here, and I'm going to put it down here, and I'm just going to go, okay, it's less steep, it's getting more steep, it looks something like this. What are we actually looking for? What fell? Oh, gotcha. I was like, what are we actually looking for? Do you have the zeros in the right places? And do you have the derivative as positive where it should be positive and negative where it should be negative? That's all we're looking for at this point from this kind of a deal. It's just a quick graph. You don't have to, spend 20 minutes making it look perfect. Okay? All right. Last thing, we can also estimate a derivative numerically. Now, remember that we got the derivative by starting with the slope of a secant line and getting those points as close together as we could, right? So here, if I'm trying to estimate the derivative of f at 3.2, I'm just going to look at this, and that's as close together as I'm ever going to get, right? That includes 3.2 is between them. F prime of 3.2, and it's a very poor approximation possibly, but this is the best I can do. I'm going to do 30 minus 26 over 4 minus 3 is 4. The average rate of change on that interval is 4. So my instantaneous, unless this curve does all kinds of wacky things, and it could, I have no way of knowing that it doesn't, should be somewhere close to 4. Okay? Any questions? Okay.